Right, section 10.1, oh, sorry for the shadow. Lines and segments that intersect circles. So our objective for this lesson is going to be identify special segments and lines, draw and identify common tangents, use properties of tangents. Okay, so first we need to talk about the definition of a circle. A circle is a set of points in a plane. So in one flat plane, a set of points in a plane that are equidistant from a given point. And we call this given point the center. Okay. So it's all the points, like let's consider this paper our plane. It's all the points on this paper that are the same distance from this point here, our center. And let's call this the point P so we can talk about it. So there's point P. So it's all the points that are this same distance. So if we look, it's really, we have this same distance here. So it's any of those points. So we could have this point here, this point over here, this point over here. It's all the points that are this distance right here, that are this distance away from that center. So it's any one given distance. So if I made a distance smaller, if I was looking at, instead if I squeeze this together and we looked at that distance, I could draw a circle of all the points, draw all the points that are this distance from this point P. And again, that would give me a different circle. Okay, so that's the definition of a circle. Okay, so we name a circle, we name it by its center. We name it using its center. So we would call this circle, circle P. So we would call this one circle capital P because P is its point of its center. And then we can even shorten that up, which we draw a little circle with a dot in the middle and then the point P behind it. So this right here means circle P. Circle P. It's just a shorthand way of writing it. We name it using its center. Okay. So now we're going to talk about different lines and segments that happen in and around this circle. Okay. So first of all, we have what's called a radius. So this is going to be a slightly different way of thinking about a radius from previously. Slightly different, not much. Here we're going to think about a radius as a segment. Okay, this is a little different. A radius is a segment with one end point, the center, of the circle, and other end point on the circle. So if I have one end point, here's the center of my circle, and then if I pick another end point on the circle, let's say this end point over here, let's call this R. So this segment that goes from P to R, this segment that goes from P to R is what we call a radius. Okay. So this right here is our radius. So segment PR is a radius because it starts at PR. So there are an infinite number of radii. That's the plural for radius, R-A-D-I-I. Radii. There are an infinite number of radii that I could draw on the circle. Again, just starting at the center and going to any point on the circle. Okay. That's a radius. Okay. Another type of segment is a chord. This one's new. A chord, again, is also a segment. But instead of one endpoint being the center, it's a segment with both endpoints on the circle. Okay, so it's a segment with both endpoints on the circle. So if I was to put, let's say here, let's do endpoint A, and do another one over here, B, The chord, the segment that connects A to B is a chord. So there is a chord. A radius is not a chord because this point is not on the circle. So an example of a chord here would be segment AB. This right here is a chord. So let's go ahead and label. This guy here is a chord. This guy here is a radius. Okay. So now we have a diameter. A diameter is a special type of chord. A diameter is a chord that contains the center. So if I draw a chord, so basically both endpoints, let's go B here, and let's go through the center and have the other endpoint over here. So let's say the other endpoint's over here. Let's call this point C. So then BC, segment BC, is a chord because both endpoints are on the circle, but it's also a diameter because it contains the center. So a diameter is a special type of chord. Okay. Right, so all these, a radius, a chord, and a diameter, are all really segments. Okay, they're all segments. Our next one here is a secant is a line. It's a line that intersects the circle. But it has to intersect the circle in 2 points. So basically, it's a line that goes through this circle in 2 points here. Okay, so this right here is a secant. So let's go ahead and I'm going to color code the secant. So the secant is this guy right there. That green is a secant. Okay. And again, this long one here, let's go ahead and label this one long is the diameter. I'll kind of label this up. And our last one is a tangent. A tangent is also a line that intersects a circle. But it intersects the circle in only 1 point. Okay, so this means it has to come up and barely touch the circle. So it only touches at this 1 point here. And that is what we call a tangent. So again, I'm going to label this guy too. So that's a tangent. It comes up, barely touches that circle. Okay, we call this point right here the point of tangency. Okay, so this is where the vocabulary can get a little confusing because we talked about tangents back when we did SOHCAHTOA. You remember our SOHCAHTOA tangent? We had our SOHCAHTOA and this T stood for tangent. It's the same word that has 2 different meanings. Here, this is a tangent line. A tangent is referring to this line. Here, this tangent is referring to a ratio. The tangent ratio of opposite over adjacent. Okay, so it's just some differences in how we talk about them and the context in which we're talking about them. Okay, so it really means 2 different things. Okay. So we can also think of sometimes we use the word tangent with rays as well. We can talk about a tangent ray instead of a tangent line. Okay, so it just kind of depends on how we're using it. Okay, so in this next part here, they want us to tell whether these are a radius, a chord, a diameter, a secant, or a tangent. Okay, so here we have this is segment PR. So it goes from P, it goes to R. So I'm going to go ahead here and then do some highlighting. So segment P to R. Okay, so first of all, the 2 endpoints are on the circle, so I could call it a chord, but it goes through the center, so a better description would be a diameter. Yes, it is a chord because the endpoints are on the circle, but a better description of it is a diameter because then we know for sure it goes through the center. It goes through the center O. Okay, now here we have line MN. So line MN. So we're looking at this line that goes on forever, MN. Even though they don't have an arrow there, The fact that there's arrows on either end of this tells me that this guy goes on for forever in both directions. So it's a line, but it just barely touches the circle at R. Since it only touches the circle at one place, we call it a tangent. Okay. Right, now we have line PQ. So let's look at P to Q, that's this line right here, again going on and on in both directions. Okay, this goes through the circle in two places, so we would call that a secant. And then here we have QO, segment Q to O. This, it starts at the center, goes to a point on the circle, so that makes that a radius. So that makes that a radius. All right. So now we have a little bit more vocabulary. Coplanar circles. That circle's in the same plane. Again, all coplanar means is in the same plane. If I have two circles in the same plane, okay, the two circles could intersect each other at 2 points. Okay, they could intersect each other at just 1 point, or they could not intersect each other at all, like these two or these two. Okay, if they intersect each other at 2 points, okay, they're just intersecting circles. They intersect at 2 points. If they intersect at 1 point, we call them tangent circles. Okay, so we would say this circle and this circle are tangent. In this context, tangent is being used as an adjective because it's describing the circles. So didn't think you have some vocabulary today. It's describing the circles. It's describing the circles as the circles are just barely touching. Okay, they could touch each other and one be inside the other, or one be on the outside of each other. Okay. Okay, so it's just, I mean, there's two different ways for them to be tangent. Okay, or they could have no points of intersection over here. If they have no points of intersection but have the same center, in this case, they have the same center. If they have the same center, we call them concentric circles. Co-center circles. See the co-center circles, meaning they have the same center. So these are concentric circles. Okay? So it's just basically 3 different ways that two circles in the same plane can relate to each other. Okay? So if you notice here in this, with our tangent circles, we have drawn in here a tangent line. So here we have this tangent line. Okay, this tangent we call a common tangent because it's tangent to both circles. It's tangent to the little one, it's tangent to the big one. This here is a common tangent because it's tangent to the little one, it's tangent to the big one. If the tangent is in between the two circles, like in this case, we call it a common internal tangent. Okay, if it's on the outside of the circles, we call it an external tangent on the outside. Okay. Okay, so now we can draw common tangents of circles that aren't tangent themselves. Here we have these two circles that don't intersect. They are not tangent. But I can draw a line. I can come in here and draw a line that is tangent to both of them. Tangent here, tangent here. This we still call a common tangent. Here, tangent is a noun. It's a thing. It's a line. It's a noun. Okay, so here is a common tangent because it's tangent to both circles. Okay, I could also draw one on the other side and have a common tangent there. Okay, we could also draw one that crisscrosses in the middle. Okay, so this is on the outside. It's not happening in between the two circles, So this is a common external tangent. This one here is external. Again, external on the outside. So let's see if we can draw some common tangents to these circles. Okay, so first of all, in this case, we have one circle inside the other. Okay, and I want to draw a tangent, a common tangent. I want to draw a line that just barely touches both the inside circle and the outside circle. Okay. Okay. Well, if we think about it, if we're just barely touching the outside circle, the inside circle, it's going to have to look like this. Which, no matter how I draw it, it's always going to cross through this outside one twice. So there is no possible way of drawing a common tangent here. So this one has no common tangents. Okay. Now this one, we have one inside the other, but these two circles are tangent. They intersect at this point here. So these are tangent circles. So I could draw in a common tangent that just comes in and barely touches right here. Okay, but that's the only one there is. There's only that one common tangent. But here I have two circles kind of away from each other. So we know from up here we could draw one on the outside like that above. So I could draw a tangent line up here like this. Okay, there's one. This one here is external, right, because it's on the outside. Okay, but I could also draw one down here on the bottom side of it. So again, two more points of tangency. Again, this one here is also external. So there's two. But I could also crisscross here in the middle, meaning I can draw one that goes between the two. So it'd be one like this. Again, tangent, I'll pretend. Tangent there, tangent here. This one here is internal because it's in between the two circles, in. Okay, and then we could have this one here that also goes the other direction. Intersects here, intersects here. This one here is also internal. So I was able to draw 4 common tangents in this case. I was able to draw 4 common tangents. Okay. All right, so now that we know what tangents are, we can talk about these tangents. Okay. We have a couple theorems. One is our tangent line to a circle theorem. In a plane, so we're talking about just strictly in a plane, a line is tangent to a circle. So if I draw a line tangent to a circle, let's call this line L. A line is tangent to a circle if and only if the line is perpendicular, again perpendicular, 90 degrees, to a radius of the circle at its endpoint on the circle. Meaning, if this is a tangent, the radius drawn from this point of tangency, this radius is perpendicular. Okay. So, and this is an if and only if, meaning it goes either way. Meaning line L is a tangent of this circle. Let's call this point circle P, call this point Q. We know that line L is a tangent to circle P, if and only if segment PQ is perpendicular to line L, meaning this radius is perpendicular to line L. So whenever I have a tangent, I can draw a radius in and have perpendicular. Okay, that's really awesome, because then if I have a 90 degree, I can make some triangles out of this guy. See, I can make a triangle here. I can make a triangle any which way I want because I have a 90 degree angle. And if we have a 90 degree angle in a triangle, we can use all our SOHCAHTOA, all that awesome stuff. Okay. Right, so then here's our other theorem. This is our external tangent theorem. Tangent segments from a common external point are congruent. Meaning, if I have a tangent here, and I have a tangent here, and they intersect at this point here. Let's call this point Q, circle P. Then this point of tangency, here's my point of tangency. Let's call this point R. Let's call this point S. So tangent segments. So this segment from Q to R, that tangent segment, and this segment from T to S are from this common external point. They're congruent. So we know QR is congruent to QS. So if I have some point out here, this tangent is the same as this tangent. This idea in thought is used a lot in satellites and astronomy. We have Earth, satellite rotating around Earth. This is equidistant from both this point and that point. Okay, 2 points on Earth. Okay, very, very useful. Okay, all right, so let's go ahead and let's do a couple problems using these. Okay, first of all, is ST, this ST, tangent to circle P? So we're looking, is this tangent? So I'm going to go ahead and I'm going to extend this line out so I can see the whole tangent. Okay, so if this was tangent, this here, first of all, PT is a radius. This guy right here is a radius. P to T, okay? If this was tangent, we have a radius coming from this point of tangency, then this angle, S to T to P, this whole angle here would have to be 90 degrees. So basically we need to check, is angle STP, is the measure of angle STP equal to 90 degrees? So we're looking, is this a 90-degree angle, is what we're trying to find out. So to do that, I'm going to use the Pythagorean theorem to see, is a squared plus b squared equal to c squared? Again, that only works in 90-degree angles. So I'm going to check, is 44 squared plus 24 squared equal to 51 squared? Question mark. Is it equal? So then we go ahead and grab our calculator. 44 squared plus 24 squared equals 2512. 51 squared is 2601. So no, it is not tangent. Basically, if we zoomed in farther, we'd be able to see it crosses at more than one point. Just double checking. Yep. Okay. So here's now example 4. In the diagram, point P is a point of tangency. So they tell us it's a point of tangency. So I know line PQ is a tangent. So since it is a tangent, then I know that the radius from O to P here makes a 90-degree angle here. Find the radius of angle R. So here I have a right triangle right here. With one side is 36. This is a leg. One leg is R, so here's a leg, and then this whole thing is the hypotenuse. We know this part is R, this part is 24, so the whole hypotenuse is R plus 24. So now this really just becomes an algebra problem because I know a squared plus b squared has to equal c squared. So let's have this be a, this be b, this be c. So we'd have r squared plus 36 squared equals r plus 24 squared. So now I need to take r plus 24 and square it. That's r plus 24 times r plus 24. Again, algebra, a bit of algebra review. So let's distribute the r. We'd have r squared plus 24r plus 24r. 24 times 24 is 576. Ooh, out of room. So here I have r squared plus 36 equals this. So r squared plus 36 equals r squared. 24 and 24 is 48r plus 576. Okay, I'm now going to subtract the r squared from both sides. So those add out. 36 equals 48r plus 576. Oh, I forgot to square the 36. Oh, 36 squared. Oopsies. It should be 1296. I'm like, wait, I'm going to get a negative. 1296. Now I'm going to subtract the 576 from both sides. We get 720 equals 48r. Divide both sides by 48. 720 divided by 48 gives me 15. So the radius of this ends up being 15. Okay. Right, and then this very last example, JH is tangent to circle L at H, and JK is tangent to circle L at K. So here we have the second idea here. I have two segments tangent from the same point. So J to H is tangent, J to K is tangent, so I know these two segments are congruent. So I know 7x minus 23 is going to equal 61. Add the 23 to both sides. (84) divide both sides by 7. 84 divided by 7, we get 12. So x is equal to 12. All right, now we have one little small construction in the next video.